Hi everyone, my name is Maxim Samarin. I'm a PhD student in machine learning at the University of Basel, and I'm happy to present our work on learning conditional invariance through cycle consistency at GCPR 2021. This is joint work with Vitali Nesterov and our collaborators Mario Visa, Alexander Wiczorek, Sonali Babu, and Volker Roth. There can be different notions of invariance. In our work, we take the point of view of level sets, which are typically given by an implicit function. Think of the equation of circles or ellipses, like on the right. Our goal is to learn a representation which separates property y, like the dashed red line on the right, and explicitly controls traversal in such a level set, like angle theta on the right. So we'd like to identify a sparse parameterization of level sets, or in other words, the fewest number of parameters or knobs which control walking on such a level set. In addition, we would like to have a generative model which allows sampling of novel data points lying on such a level set. As a more practical application example, you can think of targeted molecule discovery where we would like to generate new molecules with desirable properties. Our approach can be viewed as a supervised disentanglement approach with separated latent spaces. On the right, I show you the base model, which is a variation autoencoder-like setting with an additional decoder branch for the property and two disjoint subspaces Z1 and Z0, where Z0 only decodes property Y and the full latent space reconstructs X. In contrast to unsupervised disentanglement, in our work we want to disentangle with respect to a chosen property Y. This involves the notion of conditional invariance. By fixing a property y, we fix coordinates in z0, and with sampling in z1, we can generate novel data points x with a fixed property y. Or more formally speaking, by fixing z0, we render random variables y and x conditionally independent. There exists already some work in that direction with the symmetry transformation information bottleneck, which I will refer to as the STIP in the following, and the conditional subspace VAE. Both of these approaches enforce conditional invariance through adversarial training, while in our work we use cycle consistency of property prediction to enforce conditional invariance. We take an input x and process it through our neural network to obtain reconstruction x hat and the predicted property y hat. In a second step, the cycle step, we pass x hat through the encoder once more and decode property y hat prime. And ideally, both x and its reconstruction x hat should yield similar values, y hat and y hat prime. And their discrepancy we measure with the L2 norm as our cycle consistency loss. In addition to reconstructing, we also uniformly sample in the full latent space to obtain the orange data points and in the Z1 subspace to obtain the cyan data points at fixed Z0 coordinates or a fixed property y hat. As explained on the previous slide, we now pass the new batch of data points through the encoder once more and calculate the property y hat prime and measure the cycle consistency loss between these property values. Now, if there were information about the property encoded in Z1, this would lead to an increased cycle consistency loss. So training with this additional loss moves information about the property into the subspace Z0. Additionally, the in addition sampled data points regularize the latent space structure as they also need to adhere to the cycle consistency. All of this leads to our cycle consistency enforcing conditional invariance, and that a sparse and semantically structured latent representation with respect to the property is learned. To test our approach, we consider a rather simple synthetic experiment where level sets of ellipses or ellipsoids are our property y, which can be viewed as the color in the bottom plot, to which we add some noise. In addition, we map x and y into higher dimension to make the task more difficult. As our practical real-world example, we choose small organic molecules of the QM9 dataset with known physical and chemical properties, and we pick the bandgap energy as our property y. We compare our approach to the beta VAE model, which can be viewed as our base model with an added decoder branch and a split latent space, and the STIP, which enforces conditional invariance through adversarial training. We train all of these networks to attain similar reconstruction and prediction errors for x and y, but newly generated samples have the smallest deviation from the target property value only in our model. Inspecting the latent space structure more closely, we calculate the sample standard deviation in each latent dimension, depicted in orange, and compare it to the noise in gray. And whenever the signal exceeds the noise, we consider a dimension to be selected. So we see that only our model picks the right number of parameters, which is 2, and radial and an angular component, and also learns them in the right subspaces. And if we now fix 10 different values in there's a Z0 property subspace, which is the same as saying that we fix 10 different property values, which are depicted in the different colors on the right. And we now sample in the selected 8th latent dimension. We see that this traversal reconstructs the full ellipse curves. And the bottom right corner plot samples in all selected Z1 dimensions. As we only select one dimension, this is exactly the same plot as on the left. We see a qualitatively similar result for the ellipsoids experiment, where only our model selects the right number of parameters, which is 3, with one radial and 2 angular components. And we see that in the 6th latent dimension, something similar to the polar angle is learned, and in the 8th latent dimension, a representation of the azimuth angle can be viewed to be learned. And sampling in these two selected latent dimensions reconstructs the full ellipsoid surfaces again. So although all of these networks perform similarly what concerns reconstruction and prediction of x and y, only our model selects a sparse and interpretable parameterization. The improved conditional invariance now allows us to select target molecules with a target bandgap energy, denoted with a star here, with the targets given in the left column, and to generate new molecules with a similar bandgap energy as you see in the middle. On the right, you see the target value denoted with a star, and in the shaded area, the model error for predicting the property, and the box plot provides the distribution of bandgap energies for the sampled molecules, where we see that the value of these samples is very close to the target bandgap energy and much smaller than the model error. So in summary, we combine a VAE approach with sparsity constraints, which I didn't go too much into detail in this presentation, with the idea of separating latent space Z into a properties subspace Z0 and an invariant subspace Z1 by enforcing invariance by a modified cycle consistency constraint. Our model performs model selection, as our results demonstrate that the more appropriate and the more interpretable sparse latent representation can be learned. And also our model facilitates informed latent space exploration that exhibits improved invariance properties. And with this, also in the name of our co-authors, I would like to thank you for your interest in our work.